Hi everybody, welcome to another video in Calculus 3, section 15.7, maximum minimum problems. This is going to be a very long section. So before we go to Calculus 3, let's review what we have in Cal 1. So we have critical number. So critical number or critical point is a number in the domain. So there are three things. It must be in the domain and the derivative equal to 0, or the derivative does not exist. Right, so that is critical number. And the critical number could be maximum, could be minimum, or could be just a point. Right? So, and we have first derivative test using the sign chart. And then second derivative test. We will not use the first derivative test, explain why in a minute, but we have the second derivative test. What we have here is where the first of all, it has to be a critical number. So for the second derivative test, we must have derivative equal to 0. We don't have the does not exist. If the first derivative does not exist, there will be no second derivative. So for the second derivative test, we require the derivative to be equal to 0. Does not exist doesn't work. So only equal to 0. Now if equal to 0, we have derivative, second derivative greater than 0 and less than 0. Now, the way I remember this is, if it is positive, the graph open up and we have the minimum. If it is negative, it is concave down and there is the maximum. So that is the second derivative test, and is equal to 0, it is inconclusive. So this is what we have in Cal 1. Now, and I did say that why the first derivative does not work in function of multivariable, because if we have the function of one variable, we can have decreasing and then increasing, and of course there's obviously a minimum. However, the function of multivariable, it will not be more than that, because approaching the point, it can be a different path to it. I'll give you an example. So this look like a whole shadow. Now, in this way, this is the lowest point, right? So, but if we look in this direction, that one is the highest point. So, because in function of multivariable, it can approach the point from different way. For one variable, it from the left, from the right, we can determine the minimum by decreasing and increasing. But for more than one variable, we cannot do that. So there's no first derivative test, there's only second derivative test. Because of that reason, there's the path approaching to a point is a lot of different paths. We cannot compare all of them. So it doesn't work like this. Right, so second derivative test is this. So second derivative positive, concave up, this minimum. Second derivative negative, concave down, maximum. But we do have the derivative have to be equal to 0. Right, now this is the proof. Of course, if it concave up is minimum and concave down is maximum. But I just attempt at the proof using the Taylor series. So the Taylor series is given by this. By the way, I realized that there will be a lot of things. If you did not bring this out, just need to write a few things. Don't need to write any of this. Yeah, I'll tell you what important that we need to know. But this is just a review. I'll show a Taylor series centered at the point C is like that. Now, let's just ignore on the third derivative, and we're going to have just this second term. And then also we did say that the derivative equal to 0, right? this term equal to 0. So that's one gone. And assume that the third derivative and higher, that also cancel out. So we just have f of c and this. Right? Now, x minus c squared, this term always positive. Of course, if x equal to c, it is equal to 0. But I just say, for every x near c, that means it is not equal to c. If x equal to c, this is equal to 0. But it is near it, so it's going to be positive. Now, if we have the second derivative, now we focus on the second derivative here. If it is positive, then we have f of x equal f of c plus something positive. Think about that. So which one is bigger? F of x equal to f of c plus something positive. So obviously f of x is going to be bigger, right? Because the smaller one plus something positive is going to be something bigger. So in that case we have the minimum, because f of x less than or equal to f of c. So f of c is the smallest one of all, which is the minimum. Likewise, if f of second derivative is less than 0, we have something plus something negative. So f of c have to be greater than this, because after it subtracts something, it equal to. So if they don't subtract, it will be less than f of c is going to be greater than f of x, therefore it's local max. Alright, so that's my term of the proof. When you think about that, it actually makes sense. But like I said, a little bit advanced. Besides, we don't go to Taylor series for function of multivariables in the book. So again, right, next we define the local max and local mean of the function of multivariables. Same way, if it is less than or equal to, if f of xy, for every xy this is less than, then this must be the maximum because it is bigger than everything else. And if we have this, it is less than every point xy, it is local minimum. Now, the idea is when we compare the maximum and minimum, this is the local max or min. We just need in some open disk. Now, I will not draw this in multivariable. Just look at this function. This is the local maximum. We only compare it to the point around it. We don't compare this point to that point. Right? So we just compare that on a small open disk, a very small neighborhood of it. And if it is the highest one, it is the maximum locally, because we don't compare to that point, the whole domain. If we only compare on the small neighborhood of points, then that is the local, either max or mean. If it is either max or mean, we call that local extreme values. Right, now this is what we need to know, which is right. If it has the maximum, minimum, and the partial derivative exists, then the partial derivative equal to 0. Right. But what you need to write out if you don't bring this out is this. We have an interior point in the domain, so the point has to be in the domain. We define critical point if the partial derivative equal to 0 or one of those does not exist. And the critical points, of course, is the candidate for maximum, minimum. So partial derivative equal to 0 or does not exist, exactly like what we have in calculus 1. Partial derivative, derivative equal to 0 or does not exist, and it has to be in the domain. Right. So that is exactly like how 1, but we define that for function of more than one variable. Right. Now this is new. A shadow point. A shadow point is a critical point. If there's an open disk, any open disk, there will be a point greater than it, and there will be a point less than it. case in point, this is a saddle, because compared to that path, this is the minimum, but compared to the different path, it is the maximum. Right, show that the hyperbolic function has a saddle 0, 0. So, and they said, what's big deal? What is the big deal? The saddle point is just a point where something is neither max or min, right? No. The important thing about the saddle point is it is a critical point, meaning that the partial derivative has to be equal to 0 or does not exist. Right. So it is the function will take the derivative with respect to x. Derivative is respect to y, negative 2y. And we put, if we make the partial derivative equal to 0, we have x equal to 0 and y equal to 0. Show the point 0, 0, make the partial derivative equal to 0, therefore it is a critical point. But at this point, it's difficult to determine if it is a saddle or not. But we just say in one direction, this is the minimum, and in the other direction is the maximum. So just like the saddle we have here. Right, it has to be a critical point to be a saddle point. So that's why it's special. Yeah. Right now we don't show it mathematically, so we just say in one direction it is the maximum, and in the other direction it is minimum. So it is the critical point. Right. So there is a point greater than it, and there is a point less than it. That is the saddle point. Right. Now find the critical points for this. So it's very simple. Take partial derivative, let that equal to 0. Exactly like what we did in kind 1, derivative equal to 0 or does not exist. But this is a polynomial, so we don't have the does not exist case. But we still need to solve for the partial derivative equal to 0. So first find partial derivative. Derivative with respect to x is 2x with respect to x, so this will be minus y squared. Derivative with respect to y, 4y minus x times 2y. So we have 4y minus 2xy. So those are the partial derivative. Right. Next, to find critical point, we're going to make the partial derivative equal to 0. So we have f of x equal to 0 and f of y equal to 0 to find the critical point. Right, f of x equal to 0, we have 2x minus y squared equal to 0, and then we have f of sub y for y minus 2xy equal to 0. Right. Now the problem with this is this equation sometimes it's not linear system of linear equation. So the way we solve that depends on the problem. In this problem, what I see here is this is 4y and then minus 2xy. So why don't we factor out the y, factor out 2y, and we can solve for y and x. So I will factor out the y or 2y. Factor out 2y, and then I will have 2 minus x equal to 0. The top one just ignore it for a moment, right? So factor out 2y, there's 2. Factor out 2y, we have there's x. So 2 minus x. Now, a product equal to 0, so each one of them equal to 0. So we have 2y equal to 0, or 2 minus x equal to 0. 2y equal to 0, so y equal to 0. Or x equal to 2. So that's good. Now, if y equal to 2, so y equal to 0, sorry. For y equal to 0, I'm going to substitute into this equation. To x minus y squared equal to 0. Now if y equal to 0, we will have 2x minus 0 square equal to 0. So x must be 0. So we have y equal to 0, x equal to 0. So the point is 0 and 0. It is one critical point. Now, for x equal to 2, x equal to 2, once again we substitute in that equation. So x equal to 2. So move the y square over, we have y square equal to 4. Taking the square root on both sides, don't forget there's a plus or minus. So we have y equal to plus or minus square root of 4 or plus or minus 2. Don't forget there's plus or minus. So x equal to 2, there's 2 values for y, so we have 2 points. 2 and 2. And 2 and negative 2. So there are 3 points, 3 critical points. Actually, we should consider the case where f of x does not exist, or f of y, I said, where one of them or both does not exist. But in this case, there's none, because the partial derivative are polynomials. Polynomials defined everywhere, so we don't have this case. That's all we have. Of course, we can test, put 0 and 0 here. That's 0 is good. 0, 0, so that's good. Now 2 and 2, that's good. 2 and 2, A might say yes. And then 2 and negative 2, that certainly works. 2 and negative 2, so negative 8, plus 8, so that's 0. Yeah, so those work. Yeah, so sometimes, of course, there will be elimination or substitution. There's a lot of different ways to solve the nonlinear system of equation. But on this problem, we just factor out from one equation and we can solve for it. So that's what we have. Right, so we know how to find critical points. So that's the first part of the section. Now, go to the second part. How do we determine the maximum or the minimum? Right. You should have this when you're taking the test. When you're taking the final, there certainly will be a question about this, because it is extremely important. This part is in the formula chart, so you should be able to see this. Right. Suppose the second derivative are continuous throughout an open disk centered at the point, and the partial derivative equal to 0. Right. The second derivative test in count 1, the first derivative has to be equal to 0. If the first derivative does not equal to 0, there's no second derivative. We have to have the first derivative in order to have the second derivative. And if we have the first derivative, it has to be 0. So make sure that it is a critical point. So the partial derivative equal to 0. We need that first. After that, we determine D. The reason we use D because that stands for discriminant. So that helps us to determine if it is the maximum or minimum. Right. So for the discriminant, if it is less than 0, it is a saddle point. If it is greater than 0, it could be a maximum or it could be a minimum. So that depends on whether we have the f of xx less than 0. Of course, this is exactly like in count 1. If it's less than 0, it open down, and there is the maximum, right? So less than 0. If it is greater than 0, it open up, and there is the minimum. And if it is equal to 0, it will be inconclusive. Right. First of all, you might say that sounds like random, right? How do we can determine? What happens if we have 3 variables or more? Then how do we determine if it is the maximum or the minimum? Right. And then what happens if we forgot that? Of course, there are a lot to think about. But actually, there is the system to this. That we not just get it randomly. But like I said, this part is in the formula chart for the final. You should have that when you take the test as well. So a more general way to think about this is where we have more than 2 variables. That is the Hessian matrix. So we put all the partial derivative with respect to x, y, xz, and so on, and then y is x, y, yz, and so on, and then so you have the idea. Put the vector, the matrix of all second partial derivative like that. After that, we define the determinant, one by one. So we take this to be d1, our delta 1, and we find the determinant of this to be d2. So we take the top one by one to be delta 1. To find the determinant of 2 by 2, that is delta 2. And then 3 by 3 is going to be delta 3. So it's always going from the top upper left entries. So with that we find the determinant, a bunch of determinants, and give us all the delta. Right. Now, on the delta, if it is positive, if all of them positive, it is called positive definite. If all of them positive, and if it's positive, behave like this, there will be local mean. Now, it is called negative definite if the delta alternating sign negative, positive, negative, positive, negative, positive, like that. It have to go from negative to positive. So alternating sign, starting from negative. So if that is the case, it is negative definite. And there's the maximum. So this is a lot more general than that. Of course, if we have d2 is equal to 0, that's inconclusive. Right. Now, if we're not talking about this now, then we will never talk about that, which is the Taylor series of function of more than one variable. So what is this? Like I said, this part is not in the book, but I write this in the note, so you have the better idea of why this come about and what happened if we have more than 2 variables. So when we have more than 2 variables, this is exactly what we have. Right, like I said, if we not talk about it now, then we will never have a chance to talk about it, which is the Taylor series. A function of more than one variable. So I start with the function of xy. F of c, instead of that, it's going to be c and d. So we have the function. Next we have the derivative. However, there's two partial derivatives if the function has two variables. So we have f of x sub x at the point. If derivative with respect to x, we have x minus c. So this is like equation potential plane. Exactly that. And then derivative with respect to y. If with respect to y, we have y minus d. That is the equation potential plane, by the way. If this is z. Right. Now the interesting part, we go to the second derivative. Right, go to second derivative. It is going to be 1/2 times second derivative, right? So we're going to have 1/2 second derivative xx. If it is xx, we're going to have x minus c squared. Then we have 1/2 fxy c at the point. And if there's a subscript x, we have x minus c. And if there's the subscript y, we have y minus d. And then we have another 1/2 fyx. This is y and x, so we have y minus d, x minus c. And then we have 1/2 fyy. So xx, xy, yx, yy. And this is y, 2y, so we have y minus d squared. Yeah. And then we can just go like that in the Taylor series. So Taylor series for 2 dimension, 2 variable, it's going to be like that. And when we have the third derivative, it will be more complicated. We have x, xy, xyx, and a bunch of different things. So that usually we just write 2. Now, even better, we can write this in the matrix form. Like I said, this is not in the book for sure. But later on, you might see this in your engineering or computer science course. Right. Now I will combine this together. Remember, I have the Jacobi matrix. The matrix of partial derivative. And then I multiply the matrix x minus c, y minus d. So in matrix form, that's what we have. Now the more bizarre one for the second derivative. But by the way, 1/2 times 2/1, this is just going to be a scalar. Now the second derivative, I'm going to write like this. X minus c, y minus d. By the way, there's a 1/2 in the Taylor series. And then we have the Hessian matrix fxx, fxy, fyx, fyy, multiplied by x minus c, y minus d. So in the matrix form, that's what we have. Because when we multiply it out, it is exactly like that. And even though it is in the matrix form, when we multiply it, it gives us the 1/1, just one entry. Right. So that is the Taylor series. And of course, we can write this in the shorthand. So this is just, like I said, if we don't do that now, then we will never have a chance to do it. So if I want to write that Taylor series in 2 dimension, in 2 variable, So this is derivative, and then dot this matrix. I just said by the way, we can call this something else too, and then plus 1/2 if we call this matrix, let's say V, the column vector, then the second derivative we have V transpose, meaning that we turn the column become the row, and then we have the second derivative. Right, like this means the matrix of second derivative times V. Yeah. So in the matrix form, I can write like this. But like I said, it is a little bit advanced at this level. But I just want to at least show you this, so when you go to what we call the vector calculus, a little more advanced than Cal 3, that you will see something like this. Alright, the bottom line is the second derivative test is just this, a little more advanced. Why it's come about, positive and negative definite, is that. Right, next, we have an example here. Use the second derivative test to classify the critical points for that function. Right? So by the way, this is the example that we did earlier. So go to the previous example on the previous page. This is what we have, the partial derivative and the critical points. So let's just write out from previous example. From previous example, we have derivative with respect to x is 2x minus y squared. We need this so we can take the second derivative. Derivative with respect to y, 4y minus 2xy. And the critical points. Zero, 0, 2 and 2, and 2 and negative 2. So those are the critical points. That's what we have from the previous example. Now we will use the second derivative test. Right. So of course, second derivative test, we need the second derivative. F of x is that. So f sub x, derivative of this with respect to x is going to be 2. Derivative of this with respect to y, f of xy, derivative of this with respect to y, negative 2y. Derivative of yx will be negative 2y because it's going to be the same. Mixed partial derivative are equal. And then f of yy, derivative of this with respect to y is 4 minus 2x. Right? So that's what we have. Now, like I said, since you can you have this in the final and in the, you should have this when you take the test. So we will just calculate discriminant. Of course, if we put this in this matrix, fxx, fxy, fyx, fyy, this is just the determinant 2 by 2 determinant, right? fxx times xyy minus fxy squared. So we're going to put f of xx 2, f of yy 4 minus 2x, f xx times xyy minus fxy squared so we're going to have 8 minus 4x minus 4 y squared. So that is the discriminant, which is the 2 by 2 determinant of this matrix. So we have that. Next, we have the points. So we will just test them. First, at 0, 0. At 0, 0, I'm going to put everything in here. So the discriminant at 0, 0, 8 minus 4, 0 minus 4, 0 square. And this is 8. And this is positive. Now, if it is positive, then it is either max or min. The way we determine that based on f of xx. F of xx is 2, which is positive. And open up. So this is the mean, local mean. Right? So the discriminant is positive, so there's maximum or minimum, but it is fxx also positive, so this is a positive definite. So there's a local mean. Now we tested a different point at the point 2 and 2. We have 2 and 2. 8 minus 4 times 2 minus 4, 2 square. So 8 minus 8, so that is 0. And this is negative 16. And the second, the discriminant less than 0, don't need to go any further. It is a shadow point. And then we have at 2 and negative 2. Discriminant x is 2, sorry, so this is 2. And so there's 8 minus 8 minus 16. That less than 0. So it is a shadow point also. So there's a minimum and 2 shadow points. Right. So it's not that bad because we actually solve for the critical numbers and then we just test them. A full problem might require a lot more work. Right. Next, we have this example, and I should have more space for this example. So try to write extremely small. Even I will just write half a page each time. So conserve space here. Right. So first thing, of course, is the partial derivative. So we can find the critical point. Derivative with respect to x will be 3x squared. Y is constant, will be 0. And then derivative with respect to x plus 9y. Derivative with respect to y will be 3y squared and then 9x. Right. Next we will solve for the system of equation. Partial derivative equal to 0. So it means we have 3x squared plus 9y squared equal to 0, and 3y squared plus 9x equal to 0. And I don't know where this square come from, which is not there. So what can we do here? So that usually in system equation we can use elimination or we can use substitution. I'm going to use both, but when I run the paper I only use one. Alright, so let's use substitution. If we have 3x squared plus 9y, so suddenly we can solve for 9y. We can solve for y in terms of x. Right? We can solve for x in terms of y. Now, let's call this first equation, and this is the second equation. So for first equation, we have 3x squared plus 9y squared equal to 0. So that implies 9y equal to negative 3x squared. And then divide by 9 on both sides. Y equal to negative 1 over 3 x squared if we divide by 9. So we use substitution. Y equal to negative 1 over 3x squared. I'm going to substitute that back into x. Sorry, I substitute into y. So sub into 2 to the second equation. Using that, we have 3. Instead of y, we have this. I'm going to solve this in 2 different ways. I'm going to use elimination later. Right, so multiply this out, we have 3 times 1 over 9 x squared squares x to the 4th plus 9x equal to 0, and multiply everything by 9, or just 3 will be enough. Multiply both sides by 3. 3 and 3 give us 9, cancel with the 9, so we have x to the 4th plus 27 x equal to 0. Factor out x, we have x cubed plus 27 equal to 0. A product equal to 0, so we have x equal to 0, or x cubed plus 27 equal to 0. So this gives us x equal to 0, or x cubed equal to 27. So x equal to cube root of negative 27. Notice the cube root, there's no plus or minus, only plus or minus 4, an even root. So this is negative 3. So we have 2 scenarios, one x equal to 0 and x equal to negative 3. And we can substitute it back in there. Now substitute back into this. This is also from equation 1, so let's say in 1a. So sub into 1a. when we have x equal to 0, we have y equal to negative 1 over 3. Sorry, I have to write a bit small because run out of space. X equal to 0 square, so that is 0. So we have a point 0 and 0. Now when x equal to negative 3, y equal to negative 1/3, negative 3 square. Negative 3 square is 9, divided by negative, multiplied by negative 1/3. So this is negative 3. So we have x equal to negative 3 and y is negative 3. So we have those 2 points. Right. So that is where we use substitution. Right. Now, can we use elimination though? Of course. I'm just do it differently so we can actually check our answer. So from this equation, 3x squared plus 9y equal to 0, and 3y squared plus 9x equal to 0. The reason I attempted to use elimination here because those two equations kind of symmetry, but those equations are symmetric. By that I mean if I interchange x and y, this equation becomes the other equation. So x and y, if you interchange x and y, you have the other equation. Right. So for those symmetric properties, I can use elimination. Right, I will try to, let's say, eliminate, we can do this. So I will multiply this by x and multiply the bottom by negative y. Right. Or you can try something else, try to eliminate. But if you do that, you have 3x cubed plus 9x y equal to 0, and 3y cubed minus negative 3y cubed minus 9xy equal to 0. And then we can add side by side. Those cancel out. We have 3x cubed minus 3y cubed equal to 0. So what we have is x cubed, divide everything by 3, we have x cubed minus y cubed equal to 0. So factor it out, we have x minus y. So x equal to y. So we can say x cubed equal to y cubed. So x equal to y. There's some imaginary, but we're not worried about that. Take the cube root on both sides, we have x equal to y. Now if x equal to y, the rest is easy. We just put in x equal to y. So either way, we have 3x squared plus 9y, but we're going to let x equal to y. And then from here we factor out 3x, we have x plus 3 equal to 0. So give us x equal to 0 and x equal to 3, negative 3. But since x equal to y, we have 0, 0 and negative 3, negative 3. Those are the solutions. So x equal to y and 0 and negative 3. So we have 0, 0 and negative 3, negative 3 as solutions. Either way, substitution or elimination, we have the points that. Now we do the second derivative test. Second derivative test. We have the first derivative. Now let's find the second derivative. fxx. From here, the derivative with respect to x will be 6x. Derivative with respect to x, y. Derivative of this with respect to y is 9. We don't need to do fyx because fxy is the same as fyx. That's a Clairaut theorem. And then fyy, derivative of this with respect to y will be 6y. And then discriminant xxyy fxy square. So we have 6x for fxx and 6y for fyy, and then minus fxy square. So that will be equal to 36x xy minus 81. Right. Now we have 2 points. Now we test them at 0, 0. Discriminant at 0, 0 is equal to 36 0 times 0, and this one less than 0, so we have a shadow point. And now we will test at -3 and -3. Discriminant at that point. -36, -3, -3 minus 81. So that should be positive. 36 times -3 times -3 minus 81, 243. This is positive. So it is maximum or minimum. We don't know which yet. But if we go back to xx, is 6x at -3 and -3. X is -3. So this is -18, which is less than 0. So we know either max or min, but this one less than 0. So that is the local max, because that it is a negative definite. So that's a maximum, right? So -3 and -3 is a local max. Right. So it's not that bad. Right. So first, actually the difficult part is how to solve the nonlinear system of equation. Sometimes it could be complicated. Usually try substitution or elimination. Right. Next, we have this example. We do the same thing. Find partial derivative first. Derivative with respect to x will be 2x minus 4. Actually, this one will be very easy. Partial derivative with respect to y, 4y plus 4. Now to solve for Greek points. By the way, the reason we don't do the case where it does not exist, even though the way we write it down, Greek points should have the case where one of them does not exist. But since we use a second derivative test, we require the first derivative equal to 0. If the first derivative does not exist, there's no second derivative to test. Right. So that's why we only need to let partial derivative equal to 0. Actually, this one will be extremely straightforward. Derivative with respect to x minus 4 equal to 0, and then 4y plus 4 equal to 0. So this one obviously just even simple. X is 2 and y is negative 1. Put 4 divided by 2, so it's 2, 4, negative 4 divided by 4, negative 1. So we only have one point, 2 and negative 1. It's a critical point. Simple enough. Now second derivative test. So that is the first derivative. Now let's take f of xx. That'll be 2. F of xy, derivative that with respect to y, 0 or yx. Fyy, 4. Discriminant. Two times 4 minus 0 square, so it's going to be 8. Notice there's no x and y here, so we just say this positive is 8. So there's no x, y here, but we still substitute at the point 2 and negative 1. Discriminant at 2 and negative 1. Regardless, it's still just 8. There's no x and y there. And this is positive, so that will be max or min. If it's negative, shadow point. If it's positive, max or min. And if it is 0, it's inconclusive. So to determine max or min, we have to look at the second derivative, fxx. It is equal to 2 regardless of x or y. We don't have x or y to substitute in. It is positive will be a local mean. So we'll say the point 2 and negative 1 is a local mean. Right, so simple enough, right? Very straightforward. In this case, it's really easy to find the critical point. And I'll just test them second derivative test. That's positive, that's positive. Right. Now let me just want to show you real quick. If we put in the matrix form, we have 2, 0, 0, and 4. Matrix like this. And now we have 1 by 1. So delta 1 is positive. Delta 2 is the whole determinant. Is 8. 2 by 4. 2 times 4 minus 0 times 0. So both of them positive. So this one is positive definite, which is local mean. So it's opened up and that's local mean. Right, so if we put in a matrix form, we do that and then we show that it is positive definite, but we don't need to do that. Just use the discriminant like the book do it. Right, more examples. I did mention that this is very long section, right? So yeah, we're halfway to it. Right. Now we have the same another problem here. So again, for critical points, second derivative test. Simple enough, right? The concept is it's not that bad. I just want to do a bunch of examples here. This one doesn't take a lot of space. Derivative with respect to x. That's just negative y squared. And derivative with respect to y. negative x times 2y or negative 2xy. So that is the partial derivative. Right. So I just have to read the instruction again. The instruction says that we only need to classify the point. So we either tell it is the maximum or the minimum. We don't actually have to find the maximum values, meaning that we do not need to put the points back into the function and find out what actually the function equal to. So we don't need to do that. Just classify the points. That's what the question wants us to do. Right, now partial derivative equal to 0. Negative y squared equal to 0 and negative 2xy equal to 0. It sounds easy, but when we look at this, we can say if negative y equal to 0, so that means y has to be equal to 0. Now if y is equal to 0, x can be anything. If we substitute that in here, that we have negative 2x times 0 equal to 0. So x is arbitrary, so x can be any real numbers. So all real numbers, it doesn't matter. If we have y equal to 0, both equations equal to 0. That's what we know of. Right, interesting. Let's go to second derivative test and see what happens. So we have x can be anything, y equal to 0. So what is that? So if y equal to 0 and x can be anything, so that must be the x-axis. Right, do the second derivative test. G of xx, there's no x here, so that's 0. G of xy, derivative of this with respect to x, derivative of this with respect to y, negative 2y, and that's the same as g of yx. G of yy is negative 2x. Right, derivative of that with respect to y is negative 2x. Now the discriminant. Fxx 0, fyy negative 2x minus negative 2y squared. So that is 0, and then negative 2y, so 4y squared. Right, so that's just negative 4y squared. Now we have the point. By the way, we haven't write the point yet. On the point, the critical point, x can be anything but y is equal to 0. So those are the critical points, a bunch of them in that form. So at that point, discriminant equal to, at the point negative 4, y is equal to 0 square. Now if it is equal to 0, it is inconclusive. Yeah. So we just have to do one example that is inconclusive, and this one has it. So even though we have a bunch of points and indefinitely number of pawns, but it is equal to 0 regardless, because we only substitute in for y, and y equal to 0. Right. So that's all we have. Now, this is where I take more time here. So we talk about local max and min. So up to this point, what do we do? Partial derivative to find critical points, right? Partial derivative to get to solve for critical points, and that we do. After that, we do the second derivative test. Now we go to number 3. Absolute max or min. Right. So absolute max and absolute min, the only thing different is that in the definition for the local max, we will have that happen in some open disk. In here, we still have that, but for all the points in the domain, because absolute we compare to everything in the domain. So with the graph like this, this is the absolute maximum because that one bigger than everything else. Right, and there's the theorem that I forgot to write in the note. It says that we have to have a maximum if we have to have a continuous close, and the function have to be continuous, a region have to be close. In that case, we will have the maximum or minimum. Yeah. So the function have to be continuous for sure. And so the region have to be closed and bounded sets. If it's unbounded, if the function go like this, and at the end point is missing a point, in that case there's no maximum. So we require the function to be continuous on the closed and bounded. So there will be a boundary. So if it happen to be at the boundary, there will be a boundary for the max or min. So that's why I said it has to be closed and bounded. So this actually we need to write down. You need to write this down if you don't bring this out. So what we do is kind of like what we do for the partial derivative, for the local max min. Still find the critical point in R, that's the event point. It has to be in the domain. If it's not in the domain, just ignore it. And then find the maximum and minimum on the boundary. And then we compare them. The maximum is the max, the biggest one is the max, the smallest one is the min. So that should be simple enough, right? Right, so let's look at this example. We have the whole page, so hopefully we have enough space. So we still do the same thing, find critical points. Right, so first is to find the critical point inside R, inside the region. So first, find critical point in R. This is just R, not the real number. Have to be inside of R. Let's be a little more precise. Right. Let's find the critical point in the interior of R. So we're not worried about this is equal to. It have to be inside. It have to be less than 4. Right. So partial derivative equal to 0. Those things. derivative with respect to x, minus 2 derivative with respect to y plus 2 Now we will solve for it. Partial derivative equal to 0. So we have 2x minus 2 equal to 0. 2y plus 2 equal to 0. So we have x equal to 1 and y equal to negative 1. Right, it's not that bad. So we have the point 1 and negative 1. It's nice and all, but this 1 and negative 1 suddenly within this. And by the way, what is this? We have r x squared plus y squared, that's not equal to 4. So we're talking about ball center at 2. I mean raised 2 center 0. So we're talking about the ball, including the boundary and including the interior. And we have 1 and negative 1. X equal to 1, y equal to negative 1. So yes, so that point is in R, which is good. If it's not in R, we throw them away. If it's not in R, throw it away. This one is. So we find the critical point in the interior. Next, find the critical point on the boundaries. Of R. And the boundary meaning x squared plus y squared is equal to 4, right? Equal to, when we talk about the boundary. Now x squared plus y squared equal to 4. What can we do? Right. Notice the boundary of a disk. So it is one-dimensional object, right? So we're talking about the circle, not talking about the whole disk. Now if it is on a circle, then we just need one parameter because the circle is one-dimensional object. So we parameterize it. So we have one parameter. So parameterize this is easy. This is a circle. So if we want to, we can write this as an ellipse. So we can write x equal to cosine theta or t, and y equal to sine theta. And let theta be 0 to 2 pi. So what is the big deal here? Big deal is if we have x and y, two variables. Now we only write that in terms of one variable. Now substitute it back into the function. Substitute back to the function. So I have fxy equal to 2 cosine square. By the way, we here have x squared plus y squared, so this will be 4. But let's just substitute. That is 4. Because cosine square and sine square So that gives us 4. Yeah. That is 4 minus 2 cosine theta plus 2 sine theta plus 5. So that gives us 9 minus 2 cosine plus 2 sine. Alright, so on the boundary we have f of xy equal to 9 minus 2 cosine plus 2 sine. And we're going to make that equal to a function in terms of one variable only. So what is the significance here? The significance here is we start with 2 variables, now we end up with 1. If it is 1 variable, now just calculus 1 problem, right? It is calculus 1 problem. So we take the derivative, so find critical point. So derivative, it is just 1 variable now, so just regular calculus. Derivative of cosine is negative sine, so we have 2 sine theta. Cosine is negative sine, with the negative turn to positive. And derivative of sine is cosine. And like what we did before to find critical point, derivative equal to 0. Two sine theta plus 2 cosine theta equal to 0. Right, and to solve for this, I move the cosine to the other. Move the cosine to the other side. Right, and then divide by cosine and divide by 2. So we have sine divided by cosine. And then negative 2 divided by 2. So meaning that we have tangent of theta. I think we did something like this in the previous section. Alright, what is tangent inverse of negative 1? Keep that in degree mode, that's good. Tangent inverse of negative 1. Right, negative 45 degrees. Right. So on the unit circle, negative 45 degrees here. Or we can also go the opposite direction. It's there. Both of them have the tangent equal to negative 1. So theta equal to this point, negative 45 degrees. Or we can say 7 pi over 4 coterminal angle, add 2 pi to it. Or we can say theta equal to this point, negative pi over 4 plus a pi. So here we have negative pi over 4. If you add a pi to it, add a pi to it, and we go counterclockwise. We have here that 3 pi over 4. So there are two solutions, 7 pi over 4, 3 pi over 4. So those are the critical points in the boundary. Happen when theta equal to 3 pi over 4 or pi over 4. However, we still have to consider the case of 0 and then 2 pi, the boundary of the parameters. So we have 0, 2 pi, 7 pi over 4, and 3 pi over 4. Those are the points. Right. So far, what points do we have? 1 and negative 1, and those theta. Right, now collect on those points. Right. Last step is just put everything in the table and compare them. We have x and then y. The function is belong from the beginning, x squared plus y squared minus 2x plus 2y plus 5. We have the interior point 1 and negative 1. Alright, 3 pi over 4 and 7 pi over 4. So what are they? Remember, we have x is 2 cosine theta, y is 2 sine theta. There should be 4 more. Right. We do have, once again, for the parameter, we should have the boundary of the parameters, so 0 and 2 pi. So at theta equal to 0, if theta equal to 0 and x is 2 cosine and y 2 sine, let's just write x equal to 2 cosine and y equal to 2 sine. Right, theta equal to 0, put 0 in here. 2 cosine of 0 is 2. And 2 sine of 0 is 0. So that's where theta equal to 0. Where theta equal to 3 pi over 4. We just do this quickly. By the way, 3 pi over 4, 135 degrees. Right? So 2 sine, 2 cosine, 135. Yeah, we have in degree mode. Right. Then need some scratch paper. 2 cosine of 3 pi over 4. Right, cosine. So we have 2 square of 2 over 2. So, by the way, cosine, so it's negative. Negative square root of 2. So x equal to negative square root of 2. And 2 sine 3 pi over 4. Sine 3 pi over 4 is square of 2 over 2 is positive. Right. And then theta equal to 7 pi over 4. Right. 2 cosine 7 pi over 4 will be here. Cosine is positive. Then 2 sine 7 pi over 4 will be here, sine is negative. And when theta equal to 2 pi, that is the same as 0. So we have those points. Right, put everything in a calculator and evaluate. Right, I'm going to use the table. Hit stat and highlight edit, just hit enter. Oh, there's something here, so I need better clear. If there's something here, highlight the list. Do not never hit the delete key, just hit clear and enter. We clear the list, highlight the list, clear, and enter. Never hit the delete key in here. If you want to delete an entry, yes, but do not highlight this and hit delete. It will delete the list completely, and you don't want to do that. So we have 1, 2, and negative square root of 2, and square root of 2. Right, negative 1, 0, square root of 2, and negative square root of 2. Oh, shoot. What's that? Negative 1. Right. 1 and negative 1, 2 and 0, negative square root of 2, and square root of 2, and square root of 2, negative square root of 2. Right, so we have that. 1, negative 1, 2, 0, negative square root of 2, square root of 2, square root of 2, negative square root of 2. Right, next we will enter this. I will highlight the list 3. Instead of X, I will use L1. Instead of Y, I use L2. So highlight L3, very important. And I will just say L1 square. So that's for X square plus L2 square minus 2 L1 plus 2 L2 plus 5. And we have that. 3, 5, 1.4 something. Oh wait, that's 14 point something, sorry. 14.657. And that is 3.343. So obviously the maximum is here. I mean the minimum is there. And the maximum is here. So we say the maximum equal to this at x equal to negative square root of 2 and y equal to square root of 2, and minimum is equal to 3 when x equal to 1 and y equal to negative 1. So I better write down. So we say absolute max equal to, actually we should get the exact values, but we just say 14.657, that at x equal to negative square root of 2, y equals square root of 2, and absolute mean equal to 3 at x equal to 1, y equal to negative 1. Right, so it's not that bad. Just like in Cal 1, find the critical point inside and find critical point on boundary. In Cal 1, we just have the boundary 2 points on the interval. In here, the boundary is a little more complicated. So we have to parameterize. And the boundary is one-dimensional object, so we can write that as one variable. And so that's what we have. Right, now we have an application. Once again, I did mention that this is a very long section, right? Right, shipping company handles rectangular boxes, provide that the sum of length, width, and height do not exceed 96. So sum of length, width, and height no more than 96. find the dimension of the box with the largest volume. Right. Yeah, we only have one number, 96. So what can we get from that? Right. The largest volume, the volume is length times width times height. Let's use x, y, and z for length, width, and height. So which one's which? Actually, later on we'll see that it doesn't matter which one which. But for now, y is width and z is height. Right, of course we're trying to maximize that. Right, and then we just have the sum of length, width, and height is equal to 96, less than or equal to 96. Right, however, if we want to have the maximum volume, we should use the whole 96, right? Let me write that out. Since we look for, so we try to find the box with the maximum volume. Try to find maximum volume. We should let x plus y plus z equal to 96. So we take the maximum number we can get, 96, for x, y, and z. We use x plus y plus z equal to 96. And then we're trying to, of course, 3 variables. So let's show for z, 96 minus x minus y. Right. And I will substitute this back. I will substitute this z equal to into that z. So we have v is a function of x and y equal to x, y, 96 minus x minus y. So we have 96xy minus x squared y minus xy squared. And this to be maximized. To be maximized. And also when x, y, z, they cannot be less than 0, right? And it cannot be more than 96 either. Yeah, if they add up to 96, they cannot be more than 96, and it cannot be less than 0. Any measurement cannot be negative. Alright, so what can we do here? Actually, we only need x and y. We don't need z, because the function only have 2 variables, x and y. Right, same thing we did before. Find the critical points inside this, and then the boundary, and then just test them, pretty much. Right. So, partial derivative. Derivative with respect to x. That one, 96y minus 2 with respect to x, to xy minus y squared. Interesting. And derivative with respect to y, 96x minus respect to y minus x squared minus respect to y to xy. what can we do here? And next we have the partial derivative equal to 0. I'm actually writing the 2xy here and minus x squared like this instead. Right. Did I mention anything about the symmetric equation where we interchange x and y? We go from this equation to the other. This is exactly what we have here. Again, so in that case, elimination seemed like a good idea. So what do we eliminate here? Right. Actually, if we subtract side by side, actually there's something useful coming out of it. So let's subtract side by side. So let's just keep the first equation and multiply the second equation by -1. And then we add them. 96y minus 2xy minus y squared negative 96x plus 2xy plus x squared equal to 0. Right, I will add side by side. Usually kind of symmetric equation like this, elimination may be a good idea. So subtract this, we have 96y minus 96x. That cancel out, yes, and minus y squared plus x squared equal to 0. I said, how does that help? Well, let's see. We can rewrite this. We will have x squared minus y squared, right? And then minus 96x plus 96y equal to 0. X squared minus y squared is x minus y, x plus y, and then I factor out negative 96, have x minus y. I'll factor out the common factor of x minus y. We have x plus y minus 96 equal to 0. Right, if x minus y, two factors equal to 0, so each one equal to 0. So we have x minus y equal to 0, or x plus y minus 96 equal to 0. X minus y equal to 0, we have x equal to y. X plus y minus 96 equal to 0. Notice that since x and y have to be only between 0 and 96, the only case that this works is one of them is 0, right? I always say y is equal to 96 minus x, and this only works if x is 0 or y is equal to 0, right? Because x and y between 0 and 96, you put in 0, you have 96. You put 96, you have 0, which is good. If you put anything else like 1, I guess that's still fine. But if y is equal to 96 minus x, substitute here, z could be equal to 0. Because there's no room for z. Right? So let's do this. Let's check this first before we go any further. What if y is equal to 96 minus x and we have z equal to 96 minus x minus y? So we substitute in 96 minus x, and y is 96 minus x. (96) minus x minus 96 plus x. Of course, that is equal to 0. Now, either we have z equal to 0, which is not particularly helpful, right? Because if z equal to 0, we have no volume equal to 0. So that's obviously not the maximum here. So bottom line is we only have one case of x equal to y. But that's not it. X equal to y, we will substitute in either one of these equations. Now substitute back. Let's use this equation, the first one. X equal to y, so we just replace 96x minus 2x squared minus x squared equal to 0. Because x equal to y, so we have 96x minus 3x squared equal to 0. Factor out x. We have 96 minus 3x. So we have x equal to 0, or x equal to 96 minus 3x is 0, so x equal to 32. So if x equal to 0, x equal to 32. And x equal to y, so we will have 0, 0, or 32 and 32. Because x equal to y. Right, finally, what is z? 96 minus x minus y. So add 0, 0. Z is equal to 96. Add 32 and 32. Z is equal to 96 minus 32 minus 32, which is also 32. And finally, we put in the table x, y, z. X equal to 0, z will be 96. All of them is 32. Or we have the case of y equal to 96 minus x. So when z equal to 0, and I just say one of them is x, the other one is 96 minus x. But that doesn't matter though, because what we try to maximize is x, y, z. If one of them is 0, we have 0, 0 here. The only case that have the any values is 32 squared here, which is the maximum. So max volume is equal to 32 cubed, where the size is 32 times 32 by 32, and that is for the box of 32 by 32. Right, so I said quite a lot of work, but we have x, y, z. Do that, so we only have x and y, still a function of two variables. So when we're trying to find the maximum and minimum, we have to look at the boundary, and that's, you said we haven't considered the boundary here, right? Actually we did. Well, we have 0, 0 here, so we did actually touch the boundary. And so we find all the points. Point happen to be 0, 0, 96, and then on 32, and that's the only case that have some form that is not equal to 0 is 32 cubed, and that happen to be the maximum. Alright, let me zoom out so we can see the whole problem. So that's as far as I can go. Right. So it's not that big. The math is quite simple though. Partial derivative equal to 0, and in this case just happen when we subtract side by side, we can factor out the common factor of x minus y, and so x equal to y, and then we can deduce the rest. So you get the idea here. If we try to maximize anything with the restriction of length, width, and height, the sum of length, width, and height, we're going to have a cube. A cube will have the maximum volume. Right. Now, this is not that complicated, but extremely long. I'm not sure it would fit in one page. Right, but the point is still the same. If we ask to find the absolute max or absolute mean, what we need to do is find the critical point inside the region and find the critical point on the boundary, and then just test them all. That's exactly what we do. First, find the critical point inside. So we take the partial derivative with respect to x would be y minus, with respect to x, it's y minus 8. There's no x here, no x there, and it's good. Just that. Derivative with respect to x, that's all we have. Derivative with respect to y will be x constant to y 12. Take derivative with respect to y, so that's what we have. And then we let the partial derivative equal to 0, and we solve for the system of that. So we solve for y. That's easy, right? And now let's substitute that in here. So that could be x minus 16 plus 12, so that minus 4 equal to 0. So if x equal to 4. So the point is x equal to 4, y equal to 8. Now, is the point 4 inside R? We need to determine that. So I will write R. Alright, let's do this. There's about 2 inches there. So let's say 4, 8, 12, and 16. 4, 8, 12, and 16. And then we have x is between 0 and 15, and y is 15 minus x. So actually 15 minus x would be the line look like this. Y equal to 15 minus x, equivalent to x plus y equal to 15. And so this equation, the x plus y equal to 15. So we have 15 here and 15 here. And x and y is going to be positive. The point 4 and 8 though. X equal to 4, so 4 and 8 is within the triangle. So the region R actually is the triangle here. And the point is inside. So we have 1 point. So that's good. Now on the boundary. There will be 3 boundaries. First, this point. Let's look at this line segment. From 0, 0 to x equal to 0, y equal to 15. 0, 15. X equal to 0, y equal to 15. So first part from 0, 0 to 0 and 15. So on the boundary. The first on the line segment. So in this case we set x is equal to 0. So because from this segment, this boundary, x equal to 0. I will substitute into the equation. So the function when x equal to 0, notice there's no more x here, right? So that's all we have. So we'll make this function be the function of y only. And that equal to 0. I mean, that equal to negative y squared plus 12y plus 160. If I want to solve for critical point for function of one variable, this is count one problem. Take derivative equal to 0. Derivative of this is negative 2y plus 12 equal to 0. So y equal to 6. And so the point is x equal to 0, y equal to 6. X equal to 0, y equal to 6. Of course, we still talk about the boundary 0, 0 and 0 and 15. Right, so that is the first line segment. Now the second line segment, let's say this portion here. This is from 0, 0 to 15, 0. And for this line segment, y equal to 0. Right, now the function y equal to 0, x times 0 minus ax minus y squared y0, right? And y0, sorry. So x times 0 minus ax, 0 squared plus 12 times 0 plus 160. So there's a bunch of 0, 1, 2, 3, gone, minus ax plus 160. So we have, and we're going to make that equal to, let's say h of, it's only x left, right? Because that one 0, that one 0, that's 1 0, so 160. So this is just a function of x. So we have h of x will be equal to negative ax plus 160. And if we want critical point partial derivative, derivative equal to 0, and derivative of this is negative 8 equal to 0. So here we have none. So no critical point. So on that line there's none. Yeah. So 0, 0. Right. Now the last one is the diagonal line 0, 15 to 15, 0. On here what we will have is x, y equal to 15 minus x. And x is between 0 and 15. So we have x is that and y is that. It's a bit complicated here. So the function x, y is 15 minus x. X still x. Y is 15 minus x. Oh, I don't like this. So we have y is equal to 15 minus x, would happen to be on that line. And then x still x. So we have substitute that in for y, that for y, that for y. Multiply them out. 15x minus x squared minus ax. And this I will just skip a step, and that should be 225. That's 15 squared. Plus 30x minus x squared plus 180 minus rho x plus 160. Right. Combine like terms. How many x squared do we have? Two. How about x? 15x minus 8 plus 30 minus 12. 15 minus 8 plus 30 minus 12. 45x. Just 45 minus 20, yeah. And then the numbers, negative 225 plus 180 plus 160, 115. Right, let's do this again because I'm not sure. So 15x minus x squared minus ax, 15 squared, so 225. 12 times 15 is 180. So negative x squared, yes, negative 2x squared. 15 minus a, 15 minus a plus 30 minus 12, so that's 25. Plus 25. And negative 225 plus 180 plus 160. Yeah, so that. And we will make this a function of, let's say, function k of x. And we take derivative equal to 0. So we have negative 4x plus 25 equal to 0. So x equal to 25 over 4, 6.125, right? $6.25, and then y is 15 minus x. So 8.75. So we have the point 6.25, 8.25, 8.75, sorry. Right. I might have make a mistake in here, but that's how we do it. I mean, the way we do it is correct. I might make some calculation error. So what are the points we have for an 8? So on 6, 6.25, 8.75, 6.25, 8.2, that's about here. So we have that point, and that point. Now, interestingly enough, does it look like line on a line here? Yes, this might have something to do with that, but yeah, that's another example in another time. Oh, or maybe not. It doesn't matter. Right, now let's just put everything in into the table. Right, stat, edit. I run out of space here, so highlight the list, clear. Right. Now, the points 4 and 8. Zero and 6. $6.25. So those are the points we find. Don't forget, we still have all the boundaries, the corners. 15, 0. So 15 and 15, 0. So we have 3 vertices and 3 other points. Now just need to go back to the function x times y, L1, L2, minus 8, L1, minus L2 square, plus 12, L2, plus 160. Alright, let's check one more time because one we done, difficult to go back. L1, L2 for x, y, yes. L1 for x, yes. L2 for y, that's correct. 12y, L2 for y, yes. Plus 160, then boom. Alright, which one is the biggest one? 196 is the biggest one. And the minimum will be 15 and 0. So after we evaluate this, we can say that the maximum is 196 when x equal to 0, y equal to 6, and the minimum is 15, minimum equal to 40 when x equal to 15 and y equal to 0. So that's what we have. Right, so like I said, I might make a mistake in here, but the way we do it is correct. Try to find the critical point inside and then on boundary. This one we have 3 boundaries. So for each one of them, because the boundary is one-dimensional objects, we should be able to write that in terms of one variable. And now we just count one problem. Take derivative equal to 0. And then take derivative equal to 0. And then same thing. Right. By the way, there's another way to do this in the next section, which is called the Lagrange multipliers, to deal with the boundary. Because in this case, the boundary kind of complicated thing here. Right. But other than that, I think we did a lot of example that will be very helpful. So, to recap, what do we learn in this section? Right. First, if we let partial derivative equal to 0, we can find critical point. Usually we not consider the case where it does not exist, because if it does not exist, we cannot use the second derivative test. If we find absolute max and absolute mean, yes, by all means, find all the values where the function, where the derivative is undefined. But bottom line is, find critical points first, and then we have the second derivative test to tell if it's the local max or local mean. Now, that is the second derivative test. Talking about this one. Now, if we want to find the absolute max or absolute mean, then we need to find differently, do it differently. Find a critical point inside and then on boundaries. This one has 3 boundaries, so we have to do each one of them. But if it is the boundary, it is one-dimensional object, we should be able to write that as a function of one variable. If it is one variable, we can just take derivative, so this is like our one. Once we have all the points put in the table, I run out of space, so I have to put the table on the calculator, and then we can find the maximum and minimum from there. Right, so that's all we have for this section. As always, thank you for watching.